Now I look at functions of several variables. Really only two variables, and the third ones get spit out, but the concept extends to if you had 5 variables or 20 variables or whatever. We're going to look at z equals f of xy, which means we're going to have functions that go from R2 to R. Since I've got 2 dimensions going in and 1 dimension coming out, I'm going to need 3 dimensions to graph if I were to graph these things. So let's start. What is an example of a function like this? Well, let's say I have f of xy equals this mess, square root of x plus y minus 2 all over x minus 3. If I want to know what f of a point is, say 4, 2, we just plug in like we always did. So f of 4, 2, plug in, simplify, I get a 2. What this means is x is 4, y is 2, z is 2. So I know the point 4, 2, 2 is on the graph of z equals f of xy. So that's the first thing we learn about functions, how to plug things in and get something out. The next thing we talk about is the domain. So let's find the domain of this function. I have x plus y minus 2 under radical, so that has to be greater than or equal to 0. I have x minus 3 in the denominator, so that means x cannot equal 3. So let's put this together and see what we have. I'm going to simplify this x plus y minus 2 greater than or equal to 0 so I can figure out how to graph it. When I solve for y, I have y is greater than or equal to negative x plus 2. Super duper, that's a line. I know how to graph a line. It's or equal to, so it's a solid line. I just have to figure out which half plane to cover. Well, if I plug in the point 0, 0, 0 is greater than or equal to 2. No, it's not. So the half plane that contains 0, 0 will not be colored. So this is what I get. What's going to happen as you put in points closer and closer to 3? You're going to get 0 on the bottom. 0 on the bottom means we're going for infinity, either up or down. But it's going to zoom up to infinity, so you've got kind of like this giant wave going up and this wave going down. Let's try another one. How about f of xy equals x plus 3y plus 2? Nothing wrong with this. I can stick anything in. The domain is R2. Notice the x isn't squared, the y isn't squared. This is what we call a linear function. No, the graph of it is not a line, unfortunately. Bad choice of name. But it does mean it's flat. This is going to be a plane. How about this one? I have x times natural log of x squared minus y. The x squared minus y has to be strictly positive. So I have x squared minus y is positive, which means y is less than x squared. I know y equal to x squared is a parabola, so I'm going to need a dotted parabola, and then I need to figure out which part of the plane to shade in. So imagine I've got the y-axis. So anything on the y-axis where y is positive, like say y equals 5 and x equals 0, well, 5 is not greater than 0, so the top part of the y-axis can't be part of the shaded in region, so that means below or outside of the parabola. So everything except what's on the inside of this parabola. How about this one? We have the square root of 25 minus x squared minus y squared. So z is equal to that. I have a radical, so 25 minus x squared minus y squared must be strictly greater than or equal to 0. Simplifying it so I can see what I've got here, x squared plus y squared is less than or equal to 25. Hopefully you recognize that as a circle with radius 5. And it's the inside of the circle, including the boundary. Probably didn't need to draw that. You probably know what a circle is. Now, I'm just curious, what's the graph of this anyway? What is the graph of f of xy equal to the square root of yada, yada, yada? Well, this is going to be the top half of a sphere. And how do I know this? Well, I've got z equals the square root of 25 minus x squared minus y squared. This means z has to be positive. Now, I want to simplify this a little bit so I can see what I have. I'm going to square both sides and then simplify. Well, simplify? Is it simplifying? I'm going to move the x and the y over to the same side with the z. So I've got x squared plus y squared plus z squared equals 25. And that is the equation for a sphere with radius 5. But again, remember, it's only the top half because z has to be positive, so it's the top half of a sphere. How do these things look? I have trouble visualizing a lot of these things. There are lots of tricks to get a partial view of what's going on, but nowadays we've got all these programs that will actually graph this crap for us so we can use that to see what it actually looks like. One of my favorites is GeoGebra. What am I going to look at? We're going to look at f of xy equals x times the natural log of x squared minus y. Remember, the domain of this does not include the inside of the parabola. So this is the graph of it. I can grab it and move it around and check it out. You can see the parabola in there where it's not defined. I see that back here, up here, it's just really boring. Goes up to infinity and down to negative infinity. Here it's probably the same. Yeah, shearing up and down. But that gives me an idea of what the three-dimensional graph of this looks like. Another thing that might help you, doesn't help me, might help you, to see what these graphs look like is called a contour plot. Think of it as you're basically slicing the function up, seeing what's happening when z or k is equal to 0, what happens on the k equals 1 level, what happens at the k equals 3 level, etc. So let's do this with the function x cubed minus y. If I let k equal 0, I'm just looking at the normal cubic graph. If I let k equal 1, I have that same cubic graph, but shifted down by 1. Now keep in mind, in the 3D picture, that line is actually at level z equal 1. At k equal negative 1, I have the same cubic, but now this one's shifted up by 1. And you get the idea. They're all going to be this cubic graph, either shifted up or down, depending on what k is. And we could go crazy. That does not help me. I can't see what that looks like by looking at it. Even if I colored it in to make each level like a real contour graph, saying, oh, this level is 1, this is 2, that still doesn't give me a good picture, personally, of what it looks like. So I'm going to use GeoAlgebra again. If I plug x cubed minus y into this, I have this thing. Okay, let me make sure I have it. So xy is kind of flat, z is up and down into the picture. So you can see the cubic if you look head on, a little wavy thing going up and down. This looks slanted like this because remember do you call it the vertex? That the point of x cubed, the 0, 0 point of x cubed, keeps moving down or up depending on whether your z is positive or negative. The next thing we want to look at, because this is calculus, is limits. And this is a really gross definition, but it's the official definition, so I'm going to read it to you. Let f be a function of two variables whose domain, d of f, includes points arbitrarily close to the point ab. Then we say the limit of f of xy as xy approaches ab is L, and we write the limit as xy approaches ab of f of xy is L, if and only if, for every epsilon greater than 0, there exists a delta greater than 0, such that if xy is in the domain, and it is within delta distance of AB, that's what this 0 less than the square root blah 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 is less than delta, means it's close to AB, then f of xy, that xy, minus L must be less than epsilon. In English, maybe, I can do this in English, if you hand me an epsilon, and I draw a little epsilon ball around the limit, I can find a delta such that all the points within that delta circle will be within epsilon of the limit. Luckily, we won't be doing these kinds of proofs. You probably didn't do them in Calc 1 either, but I wanted you to see the definition of what it means for a limit to exist. Proving that limits exist in 3 space is difficult, so mostly we're going to try to prove that the limit does not exist. If your function is nice and pretty, meaning it's a normal function, that means the function is going to be continuous at that point. You only have to worry about where the function is funky. What do I mean by that? Suppose I have the limit as xy goes to 1, 2 of x squared minus y squared over x squared plus y squared. Perfectly legitimate point. First thing you do, just like when you're doing this with 1 dimensions, you plug in and see what you get. X is 1, y is 2, plug it in, I get negative 3/5. Yay. Beautiful. So the limit exists because I got a normal number. However, suppose I have the limit of xy approaching 0, 0. That's not normal. If I plug that in, I get 0 over 0. Now, you might be thinking, let's do L'Hopital, but we can't, because we have 2 variables, and L'Hopital only works with 1 variable. So what we have to do is show that this limit doesn't exist. For the limit to exist, it has to be the same along any path you take to get to 0, 0. It doesn't matter if I follow this path or that one or this one or anything. They all have to come up with the same limit. So if we can find 2 paths where the limits are different, then we have shown that the limit doesn't exist. So let's look at this one. Let's take the path along the y-axis. The y-axis means x equals 0. If I plug in x equals 0, I have negative y squared over y squared I can simplify that before taking the limit and get -1. If I go along the x-axis, that's where y equals 0, I now have x squared over x squared. That simplifies to 1 before I take the limit. Since I got -1 along one path and 1 along a different path, this limit does not exist. Let's try another one. Let's say we have xy over x squared plus y squared. Let's try the y-axis. So x equals 0, we get a limit of 0. The x-axis, y equals 0, we get, damn, that's not going to help us because they're the same. I need something different. So let's try a different path. Suppose I try y equals x. I have the limit as xy approaches 0, 0 of x squared over 2x squared. I can cancel the x squareds. That becomes 1/2. I really don't need to do the next step that I did because I just have a limit of 0 here and a limit of 1/2 there. So I already know the limit doesn't exist. But I did it on another path, so I'm going to show you that too. If y equals -x, I get -1/2. Oh look, 1/2 and -1/2 are different, so is 0. So this limit does not exist. Last limit for now. The limit as xy approaches 0, 0 of xy squared over x squared plus y to the 4th. If I go along x equals 0 or y equals 0, I'm going to get 0 both times. That's not going to help me. If I say, let's try y equals x, then I have x cubed over x squared plus x to the 4th. This is a problem in a couple ways. I can't bring these two together. I'm going to try a different path. I'm going to try the path x equals y squared. By doing that, my x becomes a y squared, so in the numerator I have y to the 4th. In the denominator, my x squared becomes y to the 4th, so now I have y to the 4th plus y to the 4th, which is good. They're both the same power. I can bring them together. I get y to the 4th over 2y to the 4th. Now simplifying, I get 1/2. If I go along the path x equals -y squared, I get the same ability to bring things together, but this time I get a -1/2. Since I got two different limits on two different paths, the limit does not exist. So now we've done limits. The next logical thing after limits is continuity. What does it mean for something to be continuous? When we were in 2 space, or when you were doing this back in Calc 1, we would say, oh, can you draw this without lifting your pencil? Not a very mathematical definition, but it worked. What does it mean to be continuous in 3 space? It's not like you can draw without picking your pencil up, but if there's a hole in your surface, then you know it's not continuous there. Let's look at the formal definition. Just like before, we say a function is continuous if the limit as you approach a point is the same thing as the function value at that point. This is true no matter if you're going from R2 to R2, or you're going from R2 to R5, or R3 to R whatever. That's the formal definition of continuity. And the places you're going to have to worry about this is with piecewise defined functions. Or when you're in higher level math, some weird ass function that some mathematicians come up with. You're not going to see those kind of functions here. For us, what we have to worry about is piecewise defined functions. So here's one. I have x squared minus y squared over x squared plus y squared. And so this function, the domain is everything but 0, 0. But at 0, 0, I define the function value to be 1. Now we already know that the limit as we approach 0, 0 doesn't exist. We did it a couple slides ago. So this function is not continuous at 0, 0. So if I give you average Joe function, and I ask you, where is this continuous? Pretty much it's going to be continuous on its domain. So I've got cosine of the square root of 1 plus x minus y. The domain, well, under the radical has to be greater than or equal to 0, which means y is less than 1 plus x. So the domain is this shaded region. At this hard line here, that's where 1 plus x minus y is equal to 0, and cosine of 0 is 1. So if we look at the graph of this, it's actually sitting up on 1. So this is the domain of the function. It's going to be continuous everywhere, except it's going to stop at the edge, but it's going to be continuous as you approach the edge. So this function is continuous everywhere on its domain. What about this one? I have e to the x plus e to the y over e to the xy minus 1. I can't have 0 on the bottom, which means e to the xy can't be 1, which means xy can't be 0. So neither x nor y can be 0. So if I graph this, it's pretty dorky. You just basically whited out the two axes. This function is going to be continuous everywhere on its domain. So everywhere except the two axes. So let's look at the big picture. When you were young, you learned about y equals f of x. You learned how to plot points. Then you learned how to take limits. Then you learned what continuity was. And you learned about derivatives. So looking at the big picture, if we let z equal f of xy, just like before, you want the biggest subset of R2 where f of xy is defined. That's going to be your domain. Basically, no negatives under an even radical and no zeros on the bottom of a fraction. Very mathematically stated there. Contour graphs. You look at k equal f of xy for various values of k to get a topographical map of your function. Limits. We're going to be proving limits don't exist at points by taking different paths to that point. And continuity. Pretty functions are continuous on their domain. Beware of piecewise defined functions. That's the big picture. So those should be the 4 takeaways from this lecture today.